Today's lecture is going to be on text classification and spam detection. We will delve into the mechanics of text classification and how it empowers us to distinguish between legitimate content and unwanted messages. Firstly, before starting learning the code, we will try to understand how to turn on the runtime. So, what we'll do is we'll just click on the runtime over here and click on change runtime type and select T for GPU over here and click on the save, connect. So as we can see, it's connecting and now we are successfully connected to GPU. Now let's start with our code. So in our first block of code over here, these lines import necessary libraries for data manipulation, model construction, and visualization. And let's start with our first main line of code now. Here we are trying to import data. So these two lines, what's happening over here is data frame named df is created by reading a CSV file named spam.csv. The data is read with the specified character encoding Latin -1. The head function is used to display the first few rows of the data frame. Over here, a binary classification setup is being prepared based on the label column in the data frame df. The variable y is assigned the value 1 if the label is spam and 0 if it's not. The train test split function is used to split the text data and labels into training and testing sets: xtrain, xtest, ytrain, ytest. In our next line of code, a tokenizer named uh, tk is created. It will tokenize the text data. The fit on text method fits the tokenizer on the training test data, preparing it for conversion into sequences of integers. Now we will see how we can use that tokenizer to transform the text. Over here, text to sequences method converts the text data into sequences of integers based on the tokens generated by tokenizer. Sectrain and sectest now hold sequences of integers representing the test training and testing text data. So this sectrain is sequence train and sequence test. So what's happening is it is now holding sequences of integers representing the training and testing text data. Moving on to our next line of code, these two statements prints like the first three sequences of integers in sectrain followed by total number of sequences in sectrain. Later on over here, what are we trying to do is we are trying to pad the sequences to each sequence in the same length. So how are we doing this is the pad sequences function is used to ensure that all sequences have uniform length of 40 by padding with zeros or truncating as needed. Sectrain pad and sectest pad now contain the padded sequences. An important note over here is the padding value, which is usually 0, can be adjusted using additional arguments of the pad sequences function if needed. Now, this statement retrieves the first two rows sequences from the sectrain pad array. This could be used to inspect or analyze the pre-processed and padded training sequences for the first two samples in your dataset. Let's check out how we'll build the model now. So for building the model, firstly we'll have to define some functions to calculate recall and precision. Let's see how we can do it. So these lines of code over here Define custom metrics for recall and precision. These metrics will be used during model training and evaluation. The calculations involve rounding, clipping, and summation, considering true positives, possible positives, and predicted positives. These functions take true labels and predicted labels as inputs and perform calculations based on these values. So let's see the K over here. It's common abbreviation used in Keras for backend functions. So this functions such as k.sum, k.round, these are the functions which are used to, round the clipped results to the nearest integer, compute the sum of the rounded values. So the k.clip right over here, what this function does is it clips the results to ensure that they are between 0 and 1. And finally, this k.epsilon is a small constant that is often used to prevent division by 0. So this is how we are trying to define functions so that we can get our values out of it. Now that we have generated functions to compute custom recall and precision metrics, let's see how we can construct a RNN model. Over here, a sequential model M is created. It consists of an embedding layer, an LSTM layer, and two dense layers. The embedding layer converts integer encoded words into dense vectors. The LSTM layer processes the sequence. The model ends with the dense layer with a sigmoid activation function for binary classification. The model summary is displayed with use of this line of code. So as we can see the result of what we have coded over here. Now index word over here is a dictionary that maps integer indices to their corresponding words. Just like that, this length of tk.index word, this specifies the input dimension, which is the size of the vocabulary plus 1 for out of vocabulary words. So this one over here we are adding for out of vocabulary words. This 32 over here in LSTM indicates the number of LSTM units in the layer, and dropout and recurrent dropout over here are set to 0, meaning there's no dropout applied between time steps and no recurrent dropout. ReLU and sigmoid, these are just activation functions which are suitable for binary classification tasks. Now moving on to our next lines of code. We are trying to compile the model over here. So the model is compiled with Adam optimizer, binary cross entropy loss function, which is suitable for binary classification, and custom metrics including accuracy, precision, and recall. This Adam optimizer right over here is a stochastic gradient descent method that is based on adaptive estimation of first order and second order moments. And binary cross entropy right over here measures difference between predicted probabilities and true labels. Let's see how we can fit the RN model now. So over here the model is trained using the training data sectrainpad and ytrain. Training is done in batches of size 32 over 10 epochs. So validation data is provided using the testing data, which is sec testpad and ytest. So after training, the fit method over here returns a RNN object that contains training metrics and loss values for each epoch, as you can see over here. We have got accuracy values, precision values and recall values for each epoch. And now we will see how we can plot evaluation metrics and graphs for each epochs. So this loop right over here iterates through the accuracy, precision, and recall metrics stored in the training history RNN.history. It plots these metrics over training epochs and validation epochs using matplotlib. The plots are customized with labels, titles, and legends as well. The loop generates separate plots for each metric as we can see over here: accuracy, precision, and recall. RNN.history right over here accesses the training metric, which is accuracy, precision, or recall. This line of code creates a range of epoch values starting from 1 up to the length of the accuracy list. It is used as x-axis values for the plots. X label and Y label kind of define the graphs X label and Y label, X axis and Y axis. And over here we can define the title, and this is how plot.legend we can use to uh, add a legend to the plot showing labels for the training and validation lines. So overall the code demonstrates the process of building training and LSTM based text classification model for spam detection. It covers data preprocessing, model construction, compilation, training, and visualization of training metrics. The custom recall and precision metrics provide additional insights into the model performance beyond standard accuracy.